This topic covers the structure and properties of peptides. So, previous topic we looked at the structural aspects of amino acids, also their chemical features, including their acid-base properties. But now we're going to look at how we can combine these amino acids together to form polymers called peptides. And we're going to look at the detailed chemical aspects of this coupling and what does it mean in terms of the overall properties of the peptides and their acid-base properties as well. So the learning outcomes are as described below. So amino acids are combined in what's called a condensation reaction. So we call a condensation reaction is where we have two molecules, A plus B, and we combine them together and we have a new product as well as water. So the two products are a part of a condensation reaction. So we have two reactants and we have two products. One of the products is water. And so in terms of amino acids, we basically combine the alpha carboxylic acid group of one amino acid to the alpha amino acid group of another amino acid to form this amide bond, this covalent linkage. And this is called a peptide bond. It's an amide bond. And a result of this, if you look at the atoms involved, we're losing an oxygen off of the carbonyl carbon and replacing it with a nitrogen of the other amino acid. And so there's your O for oxygen in water, and the hydrogens are coming from the nitrogen because at the protonated state of NH3 and in the amide form of NH you lost two hydrogens, so there's your two protons, and so there's your H2O as a result of this condensation reaction. When we bring both amino acids together, one amino acid is going to be on the N-terminus, and that's always going to have the free amino group. So that first amino acid has an alpha carbon with a side chain, that'll be amino acid number 1, and the amino group that's attached to that is our amino terminus or N-terminus. And the last amino acid, since we only have two, will have a free carboxylic acid group, and that's called the C-terminus. And so if you look at the peptide itself, we have a positively charged N-terminus and a negatively charged C-terminus. Notice we lose the charge when we couple the carboxylic acid group of one amino acid with the amino group of another, because we lose water, there's no charge on that. This amide bond that's formed, what's called a peptide bond, is in planar configuration. Everything's in a plane. There's a p orbital on this carbon. There's a p orbital on this oxygen. There's also a p orbital on this nitrogen. So the lone pairs of electrons are in resonance with this, these other p orbitals in this pi system, and so it's resonance stabilized. And so that has ramifications in rotations about this carbon-nitrogen bond. All right? That resonance is better shown here. There's a lone pair of electrons here that will form a pi bond between the nitrogen and carbon, and then the pi bond between the carbon and oxygen will break. The electrons go to the oxygen and becomes negatively charged. So this is one of the resonance structures, and you can see based on that, this carbon-nitrogen bond of this amide functional group, or this peptide bond, has partial double bond character. So rotating about this bond is more difficult because you have this partial pi bond character associated with it. Also notice you have a charge delta minus on the oxygen and a delta plus on the nitrogen there as well as part of this resonance structures they're electrically neutral at this point, but there is a partial charges associated with that. So there is a ability to have a dipole along these peptide bonds as well, which is very important when we're considering how these larger polymers of amino acids kind of fold together to form protein structures. So there's a lot involved in just this one little simple condensation reaction to form this amide bond, this peptide bond between two amino acids. So when we name this, when we hook up amino acids together, we call it a peptide. Sometimes we designate the name of the peptide by the number of amino acids. So this were two amino acids here, and so we call it a dipeptide. But it's only one amide bond, but there's two amino acids. So the number of amide bonds is always going to be n-1, where n is the number of amino acid residues, unless you close it up to make a cyclic peptide. And then you would have the same number of peptide bonds as you would amino acids. Cyclic peptides are actually very interesting molecules that can be used for a variety of applications as ligands to isolate proteins, to also used in some different antibiotics as well. So some molecules will make some cyclic peptides and it's part of their biochemistry. We don't. So here are different depictions of the peptide bond. So let's go over to the resonance structure. Again, there's a lone pair of electrons here that resonates with this carbonyl group, and I showed that in the previous slide. The resonance hybrids or resonance structures are shown with these double headed arrows. The conformation about this peptide bond can be considered either cis or trans. So for example, if we form a peptide bond or an amide bond between two amino acids, this is the alpha carbon of amino acid I, that's going from N terminus to C terminus. And the next amino acid would be I+1, and this would be the alpha carbon of the second amino acid. This is the alpha carbon of the first amino acid. This carbonyl group is from the first amino acid, but the amino group is from the second amino acid. So that's why this is called I+1 here. Okay? So here is your peptide bond shown here, which is here. Okay? And here's your alpha carbons. The alpha carbons can be considered, since this is part of a partial double bond character, we can consider that as a double bond in terms of whether we want to call the alpha carbons trans or cis relative to that amide bond between that carbonyl carbon and the nitrogen. And so if we're looking at this and consider this a double bond, we would call the alpha carbons trans because they are on opposite sides of that peptide bond. And if they're on the same side here, they would be considered cis. So there's two ways to have the alpha carbons oriented between two coupled amino acids through a peptide bond. It's either trans or it's cis. And that's a very important distinction in terms of protein structure between trans or cis. So you should recognize trans or cis conformations around peptide bonds. Okay? We'll be talking more about that a little bit later. If we go to some space filling diagrams, you can see here the pi bond orbitals that are shown here in these pi bonds above and below the sigma system, and that this pi bond gives this amide nitrogen and this carbonyl carbon double bond character. All right. Another implication of that is the bond lengths will vary a little bit as well, and so you will have little differences in the bond lengths between this carbonyl carbon and nitrogen versus a non-resonance stabilized carbon-nitrogen bond. Another important feature is to recognize that the sigma system here in this peptide bond is in a plane, and that's kind of shown here. Here's your amide hydrogen, here's your amide nitrogen, here's your carbonyl carbon, carbonyl oxygen, here's your alpha amino group of amino acid, say I, and say this is I plus 1, kind of like over here. So here's your peptide bond here. Your alpha carbons are trans. All right. If it were cis, this would have to rotate all the way over here and go on this side. But this is a trans configuration. And this is all polar, 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 polar. Everything's polar. All these atoms are in the same plane. All right. The side chains are sticking out. The alpha hydrogens are sticking out. But you can see the carbons of this amide bond are in the same plane. So it's planar. So this is a planar system. So if you were to draw the plane of this system, it would be like this. Like that. Okay? They're all in the same plane. Very important when we look at how these larger polymers will fold up. So keep in mind, cis or trans along the peptide bond. Very important. Now I want to show a little bit of nomenclature and how we give these names. I drew a dipeptide before. A tripeptide should say, okay, 3 amino acids, 1, 2, 3. N-1 peptide bonds, 2 peptide bonds, 1 and 2. Okay. N-terminus, C-terminus, or N-terminal end, C-terminal end. pH 7, this will be positively charged, this will be negatively charged. Here's your side chains. Shown here, every hydrogen and carbon is shown. When I asked in the topic of amino acids, I showed you the one diagram that's in your textbook that shows the the stick drawing diagrams. That's completely fine as well. Just make sure you draw it properly. Just don't mix the two different drawings to a point where it gets confusing, and we'll get points taken off for not drawing these structures properly. All right. So how do we name a peptide? A protein, we usually have it as a formalized name based on what it does. But peptides we can name based on their amino acid sequence. So in this case, you'd recognize that this side chain is an alanine, this is a serine, this is a valine. So we keep the N-terminal amino acid as the base name, valine, and then we rename the amino acids with a YL at the end, as shown, described here. So this becomes serol, and this becomes alanyl. So it's alanyl serol valine. So you may see some of that naming nomenclature if you read some of the literature when you're doing that. Most of the time, though, folks will just put in the 3 letter code. So it'd be ALAS-SER-VAL, and they'll call it that peptide, or the ASV peptide or something like that. But this is a more formalized naming system if you were to name it. So the base name goes with the C-terminal end, and you change the name of the amino acid to the YL, dropping either the INE, the ATE, or sometimes just the E. It just depends on the amino acid name. Just wanted you to be something to be aware of. I'm not going to ask you to name them, but I'm going to ask you to recognize them and to draw them based on their single letter code and 3 letter code. So you need to know that. Another question was asked here, what kind of pKa's do you have on a peptide? You can have quite a bit, and we'll talk a little bit about that later in this topic on determining pIs of peptides, which is a little more complicated than just the amino acids where you have at most 3 ionizable groups. With peptides you can have a lot more. So this is just a little way that I would like you to draw peptides, because it's very consistent, it's easy to grade, and it's easy to catch mistakes. So first I'd like to draw the backbone. That's the alpha nitrogen, alpha carbon, and the carbonyl group of the backbone. And so a way to do that is this up and down kind of component to it. Nitrogen, alpha carbon, carbonyl carbon, alpha nitrogen, alpha carbon, carbonyl carbon, alpha nitrogen, alpha carbon, carbonyl carbon. So if we were to do like this same peptide, the ASV peptide that we were looking at in the previous slide, this would be the backbone, and then I have to make sure I put my carbonyl groups in, right? So this is your N-terminus, this is your C-terminus. Now I'm going to add hydrogen atoms to everything in the backbone here. So I'm going to add my hydrogens to the amino group, drawn at pH 7, so it's going to be NH3+. Add our alpha hydrogens, our amide hydrogens, and for our carboxylate, we're going to finish that off by putting the formalized negative charge there, because that carboxylic acid group would be deprotonated at pH 7. So you can clearly see your N-terminus and C-terminus now. Now we're missing the side chain, so let's draw the side chain in. So your methyl group, your CH2OH group of serine, and then your isopropyl group here of your valine is attached. So there's your complete drawn amino acid structure with all your carbon-hydrogen bonds. Now you could have abbreviated this with just lines in here, but you start losing track if you're going to put a side chain in there. You kind of want to follow the drawings that were shown in the amino acid section to help you with your side chain drawings. If you were to put stereochemistry in there, it can get quite confusing, because when something's on the bottom versus the top, the wedge means something if it's dark on the bottom versus if it's dark on the top. I'm not going to emphasize whether we're just assuming these are all going to be L, so I'm not going to have you specify in the wedges here if it's drawn on the bottom or the top, but you could do that if you want to. But if you can draw it like this, I'm happy. It'll be fine. We'll assume everything's L, and the key thing is the pH, if things are protonated or not, if you have the correctly drawn structure. But be consistent in your drawing of structures. But this is a way to do it that's systematic, and you can catch yourself if you're missing any protons. If you try to do it all completely as you draw from left to right, sometimes you may miss a proton here or there. But this way you'll know you have a proper number of atoms per residue, because each residue is going to have three components in the backbone: the amide, the alpha nitrogen, the alpha carbon, and the carbonyl carbon and oxygen. So you know that's going to be the case for the residues. So here's the drawing that we had on the previous slide. No stereochemistry is shown. And like I mentioned before, if you start putting wedges in here and drawing them this way, that's completely fine. But you see the wedges kind of change in their priority. Then if it's up at the top, it's a solid wedge for the side chain. And if it's at the bottom, it's dashed. And that's to preserve the L stereochemistry. So if you made it solid R here and a solid R wedge down here, now you're changing it from a D, from an L to a D, and then you'll have alternating DL, DL, DL. That's not right. So you have to keep track if you're putting these wedges in. If you want to draw them in chicken wire diagrams, that's fine, but just draw straight lines, okay? You don't have to put the wedges in there, all right? So either way is fine, just as long as you draw your structures consistently. Heteroatoms are shown, and things like methyl groups aren't. If you just draw a stick out there, it's assuming that the end of here is a methyl group, right? The amide hydrogens are usually shown, so we like to emphasize that, but really it doesn't have to be if you just draw the side chain out, as long as you're consistent and not mixing, alpha hydrogens here on the carbon. You can just draw a stick down here, and like a straight line here and a straight line like that, that'd be valine. Leaving off hydrogen is fine, but you can't mix it up. You can't have some with it and some without it. I like it there to emphasize the importance of the alpha carbon and the alpha hydrogen group. So be consistent in your drawings. I mentioned in the amino acid topic section about the specific characteristics of proline and the cis-trans isomerization that occurs. So I showed the cis-trans isomerization around the peptide bond for amino acids in general, but let's look at the specific cis-trans bonds isomerization specifically for prolines. So here's your alpha carbon of some amino acid I, and then here is your amino acid I+1, which is proline. All right, so here is your proline residue. Here's your carbonyl carbon. Here's your alpha carbon, alpha hydrogen. Your your amino nitrogen of proline is part of the amide bond, the peptide bond that is formed between the preceding amino acid I. And so here's your peptide bond here. Here's your alpha carbon I+1, and here's your other alpha carbon of the preceding amino acid I. So alpha sub I, alpha sub I+1. Here's your double bond. It's trans, okay? Hopefully all of you can see that. I'm going to make this cis, so I got to rotate this thing along this bond to flip this up over here. That's what happens here. And since your hydrogen's going down, it's going to be popping up, and this group is going to go down. And so you see the change in the stereochemistry here at this alpha carbon position. Alpha carbon was here, now it's up here. Same side as this alpha carbon. So this is cis about this peptide amide bond. Okay, there's trans, there's cis, showing all the stereochemistry in this one. All right, if we look at this from a structure standpoint, in terms of stability, what's more stable is the cis conformation or the trans conformation, more thermodynamically stable. So typically when we look at that, we look at stereochemical clashes. If the group is too big and they start to clash if they're on the same side of the double bond, it's better if they're trans. If they're small, it doesn't matter. It could be on either side. In the case of proline here, there's all this CH2 groups up here. We still have groups here. They're going back into the screen, so it's still kind of similar. You got this kind of stuff up here around this peptide bond, and you still got this stuff here, even though it's going back and away. It's away from this carbonyl group. So you can see that it's very similar, but this is probably a little more stable because everything's kind of opposite about this peptide bond. So when we do measurements, we find out that the trans form is favored over the cis form by 4-to-1. But if this were some other amino acid, like alanine, or leucine, or isoleucine, or lysine, the trans form is favored over the cis form by 1,000-to-1. So this secondary amine aspect, the cyclic aspect of proline, affects the cis-trans isomerization about the peptide bonds. From a thermodynamic perspective, for X-prolyl peptide bonds, the cis and trans isomerization is something that can happen in a protein, whereas with other amino acid peptide bonds, it's not going to be energetically favorable to go from trans to cis. So the cis trans isomerization of prolyl containing peptide bonds is actually important. It can activate a protein but from non-functional to functional. And there's enzymes that help catalyze this isomerization to favor the formation of one form or the other when we're looking at a protein activation, say for example of a transcriptional regulator that would be involved in binding a gene promoter. it has to be in the cis or transform in order to be functionally able to bind. And so an enzyme must be activated in order to facilitate this isomerization reaction. So thermodynamically, it's capable to go from one form to the other with the assistance of a enzyme, these isomerases. So we'll see some aspects of those coming into play in regulating some biochemical pathways or gene regulation as well. So just keep in mind that in terms of if you're going to form a cis bond around a peptide bond, proline is your best bet to have a cis conformation versus anything else. Now we're going to consider acid-base chemistry again of peptides, and we're going to consider in this example the titration of the tetrapeptide glutamyl glycyl alanyl lysine, or EGAK. And here is the structure of that. I like this diagram. It shows the ball and stick diagram. Also shows the peptide bonds as these planar groups between the correspondingly coupled alpha carbons. So we have 4 amino acids, so we know we have 3 peptide bonds, and that's shown here. And we can see some charges based on the amino groups, the carboxylic acid groups, and if they have a corresponding charge, the amino acid side chain. So in terms of the side chains here, we have 2 amino acids that have ionizable side chains, the glutamic acid and the lysine. And so that's shown here and here. So if you look at this, we have 1, 2, 3, 4 molecules on this, excuse me, not molecules. We have 4 charges based on these acidic and basic groups that are present on this peptide, and drawn here, positive, 2 negative, zwitterionic form that we're looking at. So let's consider if we were to take this peptide and do a titration, what would be happening here if we look at this in terms of acid-base chemistry. So if we were to do a titration curve, you'll see something that looks like this. Now, when you start adding more acidic and basic groups, some of these transitions, when you're getting to the half equivalence point, when you're hitting close to the pKa values of these groups, they may not be as distinguishable steps. If I were to sketch this by hand, I would probably do like this. Make it more pronounced, that there's these distinctive, steps like this. I'm sketching it. I'm not doing it from a pH meter, taking these measurements for me as I'm automatically adding base to the solution. And so it's not going to be a realistic curve. So some of these curves don't look like there's plateaus in there because the pH is varying a little bit under those conditions with this molecule. But it doesn't matter. You should be able to recognize that your pKa values will be at the half equivalence point. And since you have 4 pKa groups, you should have 4 half equivalence points. 0.5, 1.5, 2.5, and 3.5, and you definitely do. And you see their pKa values shown here. Extrapolate back to the y-axis. At the full equivalence point, you completely titrate away that particular proton of that group. And so this would be your completely titrated proton for your group 1, 2, 3, and 4. So you completely protonated everything by the time you did 4 equivalence points. And at these equivalence points, you can figure out if the protein is positively charged or negatively charged because of the pKa values that will be provided to you in a structure or in a table. and assigning those pK values to your group and figuring out if it's protonated or not. So shown here is the structure of the peptide in the chicken wire diagram. Notice the alpha hydrogen isn't shown. If you wanted to put it in there, you could put a dashed wedge and put a hydrogen there. That'd be great. Okay. But if you don't want to show it, that's fine too. But don't show it here, and then don't show it, then not show it here, because then I don't know if you're recognizing it should be there or not. Here they're all gone. You don't see any of those. And glycine just has 2 hydrogens, so there's nothing there. This is fine. If you want to draw these structures like this, that's great. Notice the R group will vary. If it's stereochemistry and you want to preserve that, put a wedge. But then if it's on the bottom, put a dash wedge. If you don't want to show stereochemistry, put a line. We're going to assume they're all L. Okay? The peptide bonds are shown here in green. Green sigma bonds here. And then you got your groups color-coded accordingly. Now when you start off at low pH and you titrate away, if we were to protonate everything here, all your carboxylates would be protonated, and then we start to get the lowest pK first. We titrate this one away first, this one here, the C-terminal carboxylate. Then we'll do the glutamate, glutamic acid side chain would be second, and then the next one would be, 7.8 would be your peptide amino group. Notice in the peptide, the amino group pK is a lot lower. On the free amino acid, it's around 9 or 10. But within a peptide, it's around 7 or 8. So it does change a little bit. That amino terminus does have a lower pK value than if the amino group were in a free glutamic acid, for example. So there is a little pK altering of the amino group in peptides. The carboxylic acid group also has an effect being in a peptide situation as well. The amino group is no longer protonated, but it's now neutral because it's in a peptide bond, so it has a pK lowering effect. So notice your amino and carboxylic acid groups have lower pKa's. A lowering of the pK is due to participating of that amino acid residue in a peptide bond. But you don't need to know the reason why, but you understand that it is lower for that, and how to use this information. All right, so if we were to look at this drawing here at low pH, when we haven't titrated anything away, it's kind of shown here. I like this diagram. It shows you as everything's protonated. So your carboxylates are protonated, and your overall molecule is a +2 charge. We titrate the first carboxylate away here, and that's shown here now is a -1 charge. So once you titrate it away, that's negative. This is positive. It cancels out. Now we have a +1 on the molecule. Now we're going to start titrating this one at 4.2, and we titrate that away. Now we're left with these 2 negative carboxylates here, and hope I jumped ahead of myself. After we titrate this one here, we're looking at this position, the second titration point, where we got rid of the 2 carboxylates. So the 2 carboxylates are negatively charged and the 2 amino groups are positively charged. There's our zwitterionic form that's shown here at this second equivalence point. Now we'll titrate which one? The N-terminus amino group. And when we titrate that away and we're at a third equivalence point, our amino terminus is neutral, and we just have the positive charge on the lysine side chain. And then when we can complete the titration of that and completely titrate that away, then our molecule is now a -2 charge. And so you can see the transition, +2, +1, -1, -2. Where's 0? 0 is in between +1 and -1, and it's the equivalence point after this second titration, where we're titrating the carboxylic acid group, and then we basically are electrically neutral until we start titrating away the proton of one of the amino groups to confer a negative charge. So your isoelectric point is going to be in between the +1 and -1, and hence the average of these 2 pKa values. So it's electrically neutral, and the Pi would be the average of these 2 pKa values. the titration curve, it would be at the second equivalence of 0.6. Average these two values out, it becomes 12 divided by 2 is 6. And so there's your PI value. Okay? So this is adding one more level of complexity by adding one more pKa. But how about if there were 5 pKas or 6 pKas? The same thing applies. You can make the titration curve based on looking at the half equivalence point for the pKa values and at the full equivalence point for the transitions of the charges, and then you find the position in which the molecule goes from a +1 to -1, and that equivalence point will be your Zwitter ionic form. That's going to be your PI, and it's going to be the average of the two pKa values that flank that equivalence point. So this is a way to think of it structurally. There's also a way to think of it in terms of a systematic way of doing it, and that's shown here. We can gather all the pKa values for the different ionizable groups from the molecule and rank them from lowest to highest. Okay, so you may have 10 pKa values. It'd be tough to draw, a titration curve of that, but this is a systematic way of doing it, and it's good to practice this. But you may be asked to draw it too, so this is a good way to check and make sure your drawings are correct. So you just rank them. So just rank the pKa from lowest to highest, and the first pKa would be pKa1, that'd be your lowest one, and the highest one would be N. How many you have? If N is 5, it's 5. It's 10 pKas, it would be 10. The next step is to draw the molecule at the lowest pH, 0. That's where everything is protonated. And then you determine the charge on that molecule and call it N. So if it's a +4 charge, N is 4. In our preceding example, N was 2. Okay? Then look in your pKa values that you've listed from 1 to how many you have. Now the charge on N on the molecule may not be the same as the pKa values. Like for example, you had 4 pKa values in the previous example of the peptide, but the charge was 2. But the thing is, determine the charge at 2, that's N. Then go through your ranked pKa values, find the nth pKa, and then the next one in the list, the N+1, and average those two values to get the PI. So this is a very easy workflow to determine PI values of peptides that have quite a number of pKa values. If you only have 2, you just average the 2. But if you have 4, 5, or 6, it gets a little trickier. This will work every time. But you got to make sure you get the proper N at step number 2. And so you have to draw your structure, make sure you got that everything protonated, figure out what N is, then go through your pKa list, find the N and N+1 pKa value, average those, and that's going to be your PI. All right, so let's apply this approach to the EGAK tetrapeptide in our previous example. So here's the picture of the peptide in the Zwitter ionic form. So let's follow the steps of the systematic way to determine the PI from the pKa values. So we'll rank them from lowest to highest. So the lowest one's 1.8, 4.2, 7.8, and 10. So those are 4 pKa values, low to high. Draw the molecule at pH 0. This figure here, I modified it, so I forgot to get rid of the 0 here. But what's the charge on this molecule? Well, its carboxylic acid group is protonated here, so it's neutral, neutral, +2. So the net charge now at pH 0, consider this pH 0, is +2 of the molecule. And we're going to call now N2. That's step 2. Determine what N is. Draw the structure at low pH. What's its charge state? 2. N is equal to 2. Now we go through our list of pKa values and find N. 1, 2. 2 is 4.2, and N+1 is 7.8. So those are our 2 pKa values from our list. Let's average those 2 pKa values. We get the value of 6. So there's a systematic way of doing it, and it's useful to do it this way to test yourself. if you've drawn it correctly, you may be asked to draw the titration curve and show the species or identify the species. But this is a way to help you to determine it. If it's asked to determine the PI value from a list of pK values, you can easily do it. You just got to make sure you get the right N in step 2. That's the key. Making sure you draw it correctly. If you're off by 1, then you're going to be off in your pKa value determined, or excuse me, your pKa selection, and your PI calculation will be off. So you still got to know structure. The pKa's of the side chains I talked about in the amino acid topic section and gave you a fixed value. That's a fixed value of the side chain in the free amino acid, not an amino acid that's part of a peptide, part of a residue that doesn't have a free carboxylic acid end or a free amino end. When it's part of a residue and a folded protein, it can have different pKa values based on its chemical environment that it exists. I mentioned before the fact that you put a C-terminal residue or an N-terminal residue as part of a peptide, the alpha carboxylic acid or the alpha amino group pK will lower, and that's shown here for the alpha carboxyl group and the amino group. That it does come down a little bit. It can get to much lower than 8. Again, these are just ranges. They aren't absolute values. Things can deviate from these. But you can see some of the side chains can alter, like this cysteine here, 8.5 to 9. In some enzymes, that can go down to 5. It just depends on the active site, and we'll show some examples of that later in the course. So I don't want you to memorize these. I just want you to be aware that these pKa values aren't absolute. They're relative for the experiment done to make these measurements under those conditions. And if you change the pH of the solution or the environment in which the amino acid exists in terms of its side chain and a folded protein structure, the pKa values can change quite drastically. And that makes sense because the environment that it exists is not a free aqueous solution like a free amino acid would be in. So the values can vary depending on the chemical environment in which it exists. That's what I want you to take away from this. If we look at a titration of proteins, which are many amino acids hooked together, there could be 600 of them. What does this titration curve look like? Kind of like this. I can't see any steps anymore. It's just almost like a linear looking thing here. The steps are all so close together when you're trying to ionize a couple groups. Some may have the same pKa, so you're losing a couple charges at a given time. But the idea here is that if you have an electrically neutral species, a zwitterionic species, that would be at this intersection here where the net charge is 0. If you lower the pH lower than the PI, you're going to favor the positively charged form of the protein. If you go above the PI with the pH, you're going to favor the negatively charged form of the protein. Every protein is going to have a specific PI, and we mentioned a little bit before in the other topic sections about the role of water in hydration shells and of these ionizable groups on the overall charge of proteins. And so I just wanted to emphasize that again here, that the pH is important because whether the group is protonated or not, it's going to give a certain charge on your biological molecule. And if the pH equals the PI, doesn't matter if there's 100 pKa values or 4, that molecule is going to be electrically neutral. If that molecule is electrically neutral on proteins, then the proteins will have a tendency to aggregate together because of the hydrophobic interactions, and you lose their charge specificity that allows them to repel and to be more soluble aqueously. If we lower the pH, we can protonate those groups and make it more positively charged and more soluble in aqueous solutions. If we go to higher pH from the pI value, make them more negatively charged and make them more soluble. It depends on the characteristics of the protein in terms of its amino acid sequence, whether it's going to have a low pI or a high pI. The pH is something that will dictate whether it's going to be overall positively charged or negatively charged. And so I want you to understand these principles in terms of the pH of the solution is very important, and understanding pI values of macromolecular molecules is also important for whether it's stable or not. Whether it have an overall positive charge or negative charge which is going to be important for macromolecular recognition. So keep working on the problems and thinking about these things as you're doing the calculations, not just blindly going through, but thinking of it logically, understanding these principles of pKa values, which is intrinsic to the molecule under the given conditions, and the pH and its chemical environment and how it affects the overall charge of a molecule.